Hey guys, today we are looking at 4.5. This is going to be day 1 of 4.5 notes. Here specifically we're focusing in on solving polynomials, and then in box 4 we're getting into kind of revisiting how we sketch out those graphs using different stuff that we have learned so far this chapter, and now some different tools that we'll use here as well. So starting in box 1, we're just working on solving by factoring. This will be very familiar to us. When we're solving by factoring, again, it's going to be set equal in an equation. In this case, we want to have it set equal to 0 so that we can use ZPP to solve. And so here, I've already got started. It's already set equal to 0, so that's good. So we're just going to factor this however we know how to. I'm always going to try and look for a GCF first, which in this case, holy cow, that is a thick boy. Let's go back down here. So we have this common 4 that we can factor out of all three of those terms, which gives me a squared minus 3a plus 2 equals 0. And then I can factor what's left inside there. So if I factor out that inside that parenthesis, I've got 4 times, this ends up being a minus 2 times a minus 1 equals 0, because negative 1 and negative 2 multiply together to give me positive 2, but add up to a negative 3. So then ZPP tells me I can just set each of these factors equal to 0. A minus 2 equals 0 gives me a positive 2. A minus 1 equals 0 gives me a positive 1. So positive 2 and positive 1 give me my two solutions. This 4 that's over here, because I don't have the variable attached to it at all, it doesn't give me anything in terms of solutions. Because here, if I'm solving for A is not in that factor. So I don't have to worry about that. It's just the two factors that have A involved. For number 2, it's already isolated, getting my 0 on one side. But here I have 4 different terms. So you can check for a GCF first to see if there's something between all 3 of them. But really, anytime we see 4 terms, our brain should be going to factor by grouping. This is the only method we know so far how to factor a 4-termed polynomial. So in this case, if we're doing factor by grouping, remember what we want to try and do is get these into 2 pairs where each of those 2 things have something in common between them. So usually we'll pair we try and pair it up again, just first 2, second 2. So 2z cubed minus 3z squared plus negative 8z plus 12. I just pair them up first 2 and second 2. My first 2 do have a GCF of just z squared, which leaves me with 2z minus 3. My second pair have, well, it looks like 4 in common. But here, because again, looking forward a little bit, I know that in factor by grouping, we want my parentheses that I'm left with to be exactly the same. So I want this to be a 2z minus 3 that I'm left with. So I'm actually going to factor that negative out with it. So I'm going to say the thing that they have in common is a negative 4, because then this is a 2z minus 3 there, which is nice because now those parentheses are the same, so I can factor out that 2z minus 3 from both of those 2 terms. I'm left with z squared minus 4 equals 0. And now once I have that factor by grouping step done, I can just look at the factors I'm left with to see if they factor any further. In this case, my 2z minus 3 is done. That's as far as we can take that. But z squared minus 4 is the difference of 2 squares, which factors out into z plus 2, z minus 2 equals 0. So then I'm just going to set each of those parentheses equal to 0 to solve. So 2z minus 3 equals 0, z plus 2 equals 0, and z minus 2 equals 0. So here we get a positive 2. Here, pretty easy to see, we get a negative 2. And then here, 2z equals 3. So if I divide by 2, I get z is 1.5, or 3 over 2. So those are my 3 solutions for that problem. And that's just solved by factoring. Taking a look over here at box number 2, we have something that we'll talk about called multiplicity. Now, I've mentioned this before, and the problems that we're starting with are not going to look any different. It's still going to be just solve the equation. So here, if I'm going to solve this equation first, I would recognize that since I have 3 terms on the left side, I want to check for a GCF first. And in this case, actually, we do have something in common between all three of the terms, including a variable. So if I factor this 2x that's in common out of all three of those terms, that leaves me with x squared minus 6x plus, what is it, 2? Yeah, so plus 9 equals 0. Sorry, thinking on my feet here. So now if I factor that further, again, the parenthesis that I was left with does factor. This factors out into x minus 3 times x minus 3, right? Because negative 3 and negative 3 multiplies to get 9, but adds up to negative 6. So this is what I'm talking about with multiplicity. We have this situation here where I'm going to set each of these three parentheses equal to 0. 2x equals 0. Here, this does count as a solution because that GCF that I factored out had an x involved. It had the variable involved. But if you look at these two parentheses, they're both going to be x minus 3 equals 0. So rather than having to write it twice and say, hey, x minus 3 equals 0 and x minus 3 equals 0, we'll just do it once, and at the end, we indicate that that solution appeared multiple times. So I'll go through and still do this. So x equals 0 here is my first solution. And then here we get x is positive 3. But two of my original factors gave me that solution. So I just write in here that this has a multiplicity of 2, meaning that solution appears twice in my original equation. So that's what multiplicity is, just saying multiple times in my original equation, I got this as a solution. We could have multiplicity of a number of different things. Pretty commonly, multiplicity of 2 and 3 are probably what we'll see. Or, most of the time, we don't say that it has multiplicity of 1, meaning it just happens a single time. But we'll talk about it a little bit later, kind of what the multiplicity tells us about what the graph looks like. Okay. So number 4, this one I wanted to show you. I mean, that's the same general idea, just identifying if something has multiplicity. It's just, hey, there's multiple solutions that are exactly the same, so those have multiplicity. But we wanted to show one of these to you because it's kind of funky. So we can identify pretty easily here that number 4 has a GCF, right? All three of those terms are multiples of 4, right? They're all divisible by 4. So I'm still going to start with saying 4 is in common between all three of those terms. That gives me x to the 4th minus 10x squared plus 9 equals 0. But if you look here, it's very, very weird. We haven't factored a trinomial that's not x squared x constant. In this case, we actually have x to the 4th power x squared constant. So it's kind of weird, but we can still factor this using the same pattern because, and you'll see this in a second, if I still tried factoring this in the regular old school 2 parenthesis factoring method, where I'm trying to figure out what two numbers multiply to give me positive 9, but add up to a negative 10, which in this case are going to be negative 1 and negative 9. Right, negative 1 times negative 9 is positive 9, but negative 1 plus negative 9 is negative 10. So that part works. But what I have to do here, instead of having this just be regular x in both of these two terms, I'm going to make both of them x squared. Because what ends up happening when you do the foiling process here, and I do x squared times x squared, that's going to give me that x to the 4th. But then when I multiply the other way through, I get x squareds as the thing that are my common thing in the middle, and then negative 9 times negative 1 is still that positive 9. So it actually does still factor totally normal. It factors completely. Here I'm actually not done. I shouldn't have said it's not factored completely yet because I have 2 parentheses that I have to check and see if they factor further. And actually in this case, both of those parentheses do factor further. They're both perfect square, difference 2 squares. So I have 4 times, this is going to be, x plus 1, x minus 1, x plus 3, x minus 3 equals 0. Because again, div 2 squares, if it's x squared, if something squared minus another thing squared, it's that plus that, that minus that. So I'm going to have 4 solutions here. So here, I actually don't have multiplicity, but I still wanted to throw this one at you. So what I get here, if x plus 1 equals 0, x minus 1 equals 0, x plus 3 equals 0, and x minus 3 equals 0, that means my solutions are -1, +1, -3, and +3. And if you want to, I'm more comfortable writing it that way. If you want to write out individually like we usually do, feel free to continue doing that. It doesn't really matter to me. So in this case, even though I have multiple solutions, I don't have any multiplicity because none of those solutions are exactly the same. There's the sign difference between the 1 and the -1, the 3 and the -3. So this one actually doesn't have multiplicity. Okay. All right. So taking a look over here at box 3. Box 3 is all about finding zeros, which finding zeros is really just a different way of saying the same thing. We're still doing the same, using the same skills. But if I'm finding the zeros of a particular function, that's asking me to find the x-intercepts, which is the solutions to the equation, when it's set equal to 0, hence find the zeros. So all I have to do in this case is just kind of the extra first step that I've had in the previous problem, where I'm going to replace this f of x with a 0. So if I go ahead and do that, that's finding the zeros of this function would be saying, okay, well, if 0 equals -2x to the 4th plus 16x squared minus 32, what would be my solution? That's what finding the zeros are. So in this case, if I'm going to continue doing that, I'm going to take a GCF out. All of them are divisible. They're all even numbers. Just to make it easier on ourselves, I'm going to factor out a -2 just to make them all positive. So that's going to give me x to the 4th minus 8x squared plus 16. And again, this is kind of one of those funky ones like we had on number 4, where it's x to the 4th, x squared, and then a constant. So I can still factor this out using regular 2 parenthesis factoring. It's just that, again, these will be x squareds here instead of x to the firsts. So now the two things that multiply together to give you 16, but add up to a -8, are going to be -4 and -4. Right? -4 times -4 is positive 16, but a -4 plus a -4 is -8. So now, if I factor further, factor completely, right? Each of these 2 parentheses, they're the same, but they each factor out into, or using the difference of 2 squares, x plus 2, x minus 2, x plus 2, x minus 2. And so I do end up having some multiplicity here. We can see that this solution and, this one and this one would be the same. This one and this one would be the same. So we've got 2 parentheses that are x plus 2, 2 parentheses that are x minus 2. So I'm just going to pull out these 2 here. If x plus 2 equals 0, we have x equals -2, which has multiplicity of 2. And then here, x minus 2 equals 0 tells me x equals 2, again with multiplicity of 2. So I have 2 of those original parentheses. If I factored out all 4 of them and solved all 4 of them, I would end up with just 2 unique solutions that repeat twice. So that's finding the zeros. Now, box 4 is kind of putting all that information together with stuff that we learned earlier in the chapter. So, and I know it's been a while for us because we started the chapter back in end of November, and then we got into finals and we're getting ready for that. I think it was December we were starting this chapter. So now if we're asked to sketch the graph, and I know we sketched back in early chapter 4, and we haven't really done it since then. Sketching the graph, now when we first did this, we just looked at the end behavior and then picked out kind of like the middle point and found some other points around it. But now we've got some more skill that we can use to find particular points more easily, and then still incorporate that end behavior and that kind of stuff to make it a much more accurate graph. So first things first, let's review what we know. We found already, and I'm here as nice, trying to save us some time, this is the exact same function as box 3. So we've already solved it. We've already found the zeros, which we've talked about how the zeros are the same thing as the x-intercepts, are the same thing as the solutions of the equations that equal to 0, all of that stuff. So we've already solved this and determined that the x-intercepts of this graph are -2 and +2, and then both of these have multiplicity of 2. Now that multiplicity becomes really, really important when we're sketching the graph, because you can see I have 3 different notes over here, and we're going to discuss this, and I'll erase the graph. We know that our solutions, our zeros, are our x-intercepts. So they happen at a very particular place on the graph. That tells us where on the graph it crosses the x-axis. Now, we call it crossing the x-axis because we know it intersects the x-axis at that point. But our multiplicity tells us how it intersects that x-axis. And I've written down here some notes on kind of how I describe the way that it intersects the x-axis. It's just going to be kind of your memory of it and kind of how you interpret this. But the way I look at it, it's either going through it, it's bouncing at it, or it's hesitating at it. And I'll kind of sketch this out. So if I have, I'm just going to plot out here 3 points, 3 different x-intercepts. These are not the ones we actually graph. I was giving some examples here. If I have an x-intercept that has a multiplicity of 1, meaning it just is a single solution, that goes through. So at that point, I know that my graph is going to go through that point. Straight through is going to cross the x-axis, nothing funky happening, it doesn't hesitate, it doesn't bend at all, it just continues along its path. So we've seen tons of these. This is the most common one, is it just goes through the x-axis. We've seen these in linear equations, we've seen these in quadratics, we've seen these in exponentials back in Algebra 1. These are the most common ones. Just goes straight through. A multiplicity of 2, so if you have 2 solutions at that x-intercept, if you have a multiplicity of 2, that's where I call it a bounce, where it kind of hits that x-axis and then turns back around the other direction. So it does still intersect the x-axis at that point, but it doesn't continue on to the other side. It just hits it and then bounces and turns around. Our third option is a hesitation. So this one, if you think of it kind of like, again, bending it, it's going to slowly bend to kind of level off at that point and then still continues through. So this is kind of what I envision of it. It approaches it, it kind of slows down and curves towards it, and then kind of picks back up on the other side. And we've seen these, we've graphed some cubics. If you remember back in, I can't remember what chapter it was, maybe it was chapter 1 we did some cubics, or chapter 3 with our polynomial stuff. We looked at kind of how that hesitated and then continued through, or cube root stuff. So those are kind of the 3 main ones that we see. There are other ones, and it's really just kind of about the level of hesitation and kind of similar to our even and odd functions. When we look back at those, which I'm going to talk about in a second with our end behavior, if it's an even power, they end up going back in the other direction. So it's, it starts from the bottom, it goes back to the bottom. These could be reversed. Obviously I could have another one that goes like this and goes straight through. I could have it bounce back up. I could have it kind of hesitate and then go back. That's a bad one there. Let's try that again. It's going to go more like that and then hesitate back through. It's just doing that same action. And these are really going to be more so important once we have the graphs plotted, the intercepts plotted, and it's just kind of filling in that picture of what happens at those particular intercepts. Okay, so that's multiplicity. Some other stuff that we know, something that maybe we need to be reminded of. We know our y-intercept. That's the thing we started studying back since the first function we ever studied in Algebra 1 with our linear equations. It's always this constant, whatever that number is that doesn't have a variable attached to it. That's always the b value. It's always the y-intercept, whatever letter we use to indicate it. That number, my constant, is always the y-intercept. So here we know my y-intercept is 0, -32. Yikes. 0, -32. And then our last thing that we've talked about, again, I've kind of referenced this, but we talked about end behavior back in the first section of this chapter, back in 4.1. started writing my name, sorry. End behavior. So in this case, my function, remember the two things that determine that end behavior was the degree, whether it was an even degree or an odd degree, and whether that leading coefficient was positive or negative. So in this one that we're looking at, it is negative and even. Which remember, even tells you that they point the same direction, right? If it was odd, they pointed opposite directions. Linear, one up, one down. Even, both up, both down. And then my negative tells me what the right side does, but here in this case it doesn't matter because they both point down. So we're going to have both ends going down. Both point down. So now I can start filling in this information. I can go ahead and start plotting my intercepts, -2 and +2. I'm not going to be able to fit my -32 for my y-intercept here. So what I can do, I'm not a huge fan of it just because I usually like scaling kind of my scale for my graph the same in both directions. But it would be really, really silly to make it scaled to fit my y-intercepts and then have my x's like super duper close to each other. So I'm just going to say my y-axis is going to be scaled by, what do I have to do? By 4s in order to get -32 to fit in there nicely. Because then, since this is -2, 0, this is going to be 2, 0. Then down here at -8, that's going to be 0, -2. Sorry, -32. Because if each box is 4 units, 8 units down would be -32. So those are my important, what we'll call my critical points. So I got my intercepts, and now I can look at my end behavior. In this case, they're going to be down on both the left and the right. So we know it's going to start down on the left, and it's going to finish down on the right. So from here, it's just kind of filling it in the best you can. Now you can get more specific, and you can pick more points if you want to try and fill in kind of how steep it goes down here. As long as you have those critical points and you've got the end behavior to match, I'm fine. It doesn't have to necessarily be perfect. So in this case, I'll go ahead and do it in red just to kind of make it look a little bit different. But it's going to start down because each of those x-intercepts have a multiplicity of 2. That means it's going to approach it from the bottom. It's going to bounce. So here I'm going to go ahead and start from the bottom here. It's going to go up. It's going to bounce. It has to cross the y-axis here at this point. It's going to go back up and bounce, and then it's going to finish back down on the bottom. So it's kind of got this like swoopy M looking thing, but that would be the graph sketched as best we can. It's got our intercepts incorporated with its multiplicity. It's got the y-intercept incorporated and that end behavior. So I know that's putting a lot of stuff together. I think you only got a couple of those on your homework tonight, which is right there on the screen, page 194. 4 through 20 evens. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And have a fantastic day. We'll see you soon.